The OSPF protocol, first and foremost, is a link state routing protocol developed as a replacement for the RIP distance vector routing protocol during the early days of networking and the Internet. RIP was an acceptable routing protocol. However, the fact that RIP relied solely on hop count as a metric to determine the best route quickly became problematic. The use of hop count does not scale well in larger networks with various routes of different speeds. OSPF is a classless routing protocol that employs the concept of areas to achieve scalability. OSPF version 2 is available for IP version 4, and OSPF version 3 is available for IP version 6. The characteristics of OSPF's classless design allow it to support variable length masks. Effective, routing changes trigger routing updates. There are no periodic updates. It uses the OSPF algorithm to determine the best route. Fast convergence, it rapidly propagates changes made in the network. Scalable, it performs well in both small and large network sizes. Routers can be grouped into areas to support a hierarchical system. Secure, it supports MD5 summarization authentication. When OSPF routers are enabled, they only accept encrypted routing updates from points with the same pre-shared passwords. Administrative distance is the reliability or preference of the OSPF route's origin. OSPF has a default administrative distance of 110. The three main components of the OSPF routing protocol are: 1. Data structures. OSPF creates and maintains 3 databases. Adjacency database, creates the neighbor table. Link state database, creates the topology table. Routing database, creates the routing table. These tables contain a list of neighboring routers to exchange routing information and are stored and maintained in RAM. 2. Routing protocol messages. OSPF exchanges messages to transmit routing information using 5 types of packets. Hello packets. Database description packets. Link state request packets. Link state update packets. Link state acknowledgement packets. 3. The adjacency database can be viewed with the show IP OSPF neighbor command, the link state database with the show IP OSPF database command, and the routing database with the show IP route command. To maintain routing information, OSPF routers follow this generic process of link state routing to achieve convergence. 1. Establishing neighbor adjacency. Routers with OSPF enabled must recognize each other in the network before sharing information. OSPF routers send hello packets on all OSPF-enabled interfaces to determine if neighbors are present on those links. If a neighbor is detected, the OSPF-enabled router attempts to establish adjacency with that neighbor. 2. Exchanging link state update (LSU) notifications. Once adjacency is established, routers exchange LSU notifications. LSU announcements contain the state and cost of each link directly connected. Routers flood their neighboring routers with LSU announcements, which are immediately flooded to other directly connected neighbors until all routers in the area have received all LSU announcements. 3. Creating the topology table. After receiving LSU announcements, OSPF-enabled routers create the topology table based on the received link state advertisements. 4. Database summary advertisements, based on the received link state advertisements. This database contains information about the network's topology. An OSPF area is a group of routers that share the same link state information in their link state database. OSPF can be implemented in 2 ways. 1. OSPF single area. All routers are in a single area called the backbone area, Area 0. 2. OSPF multi-area. OSPF is implemented through multiple areas hierarchically. All areas must connect to the backbone area, Area 0. Routers connecting the areas are known as area border routers, ABRs. In OSPF multi-area, OSPF can divide a large autonomous system into smaller areas to support hierarchical routing. For example, whenever a router receives new information about a topology change within the area, such as the addition, removal, or modification of a link, the router must rerun the SPF algorithm, create a new SPF tree, and update the routing table. The SPF algorithm places significant demands on CPU resources, and the time it takes to perform calculations depends on the area's size. R2 serves as an area border router, ABR, for Area 50. As an ABR, it summarizes the routes from Area 50 into Area 0. When one of the summarized links fails, LSU advertisements are only exchanged within Area 50. Routers in Area 50 must rerun the SPF algorithm to identify the best routes. However, routers in Area 0 and Area 1 do not receive any updates, so the SPF algorithm does not run. OSPF messages transmitted over an Ethernet link contain the following information. Ethernet frame header IP packet header OSPF packet type-specific data. Each packet serves a specific function in the OSPF routing process. Type 1, hello packet, used to establish and maintain adjacency with other OSPF routers. Type 2, database description packet, contains a summarized list of link state advertisements, LSAs, from the sender, used for database synchronization. Type 3, link state request packet, sent by routers to request specific LSAs from other routers. Type 4, link state update packet, used to respond to link state request packets and advertise new information. Type 5, link state acknowledgement packet, sent to confirm receipt of link state update packets. OSPF routers transmit hello packets to multicast address 224.0.0.5 in IPv4 and FF025 in IPv6. All OSPF routers send hello packets every 10 seconds for default intervals on broadcast and point-to-point networks, and every 30 seconds for default intervals on non-broadcast multi-access networks, such as frame relay. The dead interval is the time a router waits to receive a hello packet before declaring a neighbor inactive. If the dead interval expires before receiving a hello packet, OSPF removes the neighbor from its database, flooding the database with information about the inactive neighbor on all OSPF-enabled interfaces. When OSPF is initially enabled on a router connected to a network, it attempts to do the following: create adjacency with neighbors, exchange routing information, calculate the best route, and achieve convergence. OSPF goes through these states to reach convergence. OSPF operation involves various states as it tries to achieve convergence. Down state, init state, two-way state, exstart state, exchange state, loading state, full state. When OSPF is enabled on an interface, the router must determine if another OSPF neighbor exists on the link. To do this, the router forwards hello packets with the router's ID on all OSPF-enabled interfaces. The OSPF process uses the OSPF router ID to uniquely identify each router in the OSPF area. A router ID is an assigned IP address used to identify a specific router among OSPF routers. R2 receives the hello packet from R1 and adds the root ID of R1 to its neighbor list, then R2 sends a hello packet to R1, the packet contains the router ID of R2 and the router ID R1 router in the neighbor list of the same interface. R1 receives the hello and adds R2's root ID to its OSPF neighbor list, also noticing its own router ID in the neighbor list of the hello packet. When a router receives a hello packet indicating its router ID in the neighbor list, the router goes from the init state to the two-way state. The action taken in the two-way state depends on the type of interconnection of the adjacent routers. If the two adjacent neighbors are interconnected through a point-to-point link, they immediately go from the two-way state to the database synchronization phase. If the routers interconnect through the common Ethernet network, a designated router and a backup designated router must be chosen. In the following example, because R1 and R2 are interconnected over an Ethernet network, a designated router and a backup designated router are chosen. R2 becomes the designated router, and R1 becomes the designated router. Designated backup router. this process takes place only in multi-access networks such as Ethernet LANs. Why do you need to choose a designated router and a backup designated router? Multi-access networking can create challenges for OSPF in relation to saturation of link state advertisements, creation of multiple adjacencies. Main problem: Ethernet networks could interconnect many OSPF routers on a common link. Creating adjacency with each router is unnecessary and not recommended, as it will lead to the exchange of an excessive amount of link state advertisements between routers on the same network. Intense saturation of link status ads. Link state routers saturate with link state announcements every time OSPF is initialized or when a change in the topology occurs. This saturation can become excessive. To understand the problem of multiple adjacencies, you must study a formula. For any number of routers designated as n and a multi-access network, n multiplies n-1/2 adjacencies. The following example shows a simple topology of 5 routers, which are connected to the same multiple-access Ethernet network without any type of mechanism to reduce the number of adjacencies. These routers collectively will form 10 adjacencies. It may seem like very little, but as routers are added to the network, the amount of adjacency increases noticeably. After the two-way state, the routers move to the database synchronization state. While the hello packet is used to establish neighbor adjacency, the other 4 types of OSPF packets are used during the handshake process and database synchronization. In the X-start state, a master-slave relationship is created between each router and the designated router and its adjacent backup designated router. In the exchange state, the master and slave routers exchange one or more database description packets. R2, for example, sends a database description packet to R1. When R1 receives the description, it performs the next action. It confirms receipt of the description with the acknowledgement packet, then R1 sends description packets to R2. R2 acknowledges receipt to R1. R1 compares the received information with the information. It has its own link state announcement database. If the database description packet has a more current link state entry, the router enters the loading state. For example, R1 sends a link state request regarding network 172.16.6.0 to R2. R2 responds with complete information about 172.16.6.0 in a link state update packet. Again, when R1 receives the update and sends an acknowledgement, then R1 adds the new link status entries to its link status announcement database, after fulfilling all status announcement requests. Links for a given router. Adjacent routers are considered synchronized and in the full state. Once the topological database is synchronized, updates are sent to neighbors only in the following circumstances: when a change is perceived with an update in the topology and every 30 minutes. Well, that's it for this video tutorial. I hope that this information will help you a lot to learn more about the protocols, also for study methods, for projects that we have pending, also to solve some problems when it comes to understanding a little the operation of the protocol, and for some certification exams. I hope everything helps you a lot and see you in the next video. Don't forget to subscribe.